So this last video for 7.1 is going to take a little bit of a change. So instead of simplifying using an identity, we're going to use identities to find exact values. So this is going to feel a lot more like chapter 6. So what's going to happen is you are going to be given a question where it says, use the sum and difference identities to evaluate exactly. So these should involve your exact triangles. Now, when I give you 15 degrees, you might be thinking, well, that's not one of my exact triangles. You know, my exact triangles, I know 0 degrees, I know 30 degrees, I know 45 degrees, I know 60 degrees, I know 90 degrees, and so on. Well, what's going to happen here is that you're going to be able to use these numbers with addition or subtraction to make this value. So if you were trying to get the number 15, for example, you could do 45 minus 30 or 60 minus 45 to make the 15. So let's just choose the 60 minus 45. So I'm going to replace sine of 15 degrees with the sine of 60 degrees minus 45 degrees. Well, now what? Well, now what we're going to do is we're going to turn to our formula sheet and you're going to look at the sum and difference identities. And you're going to see the sum and difference identities right here. Okay, sum and difference identities. And we're going to look at the fact that this is a sine function and it's the sine of 60 minus 45. So here we go, sine of some angle plus or minus another angle. So we're going to use minus. So we've got the sine of 60 minus 45. So what we're going to replace this with is the sine of the first angle times the cos of the second angle. Now, because we used minus, we're going to subtract the cos of the first angle times the sine of the second angle. Okay, so let's see what that looks like. We're going to have the sine of the first angle times the cos of the second angle. That looks like a 95. Minus, now you're going to switch it, the cos of the first angle times the sine of the second angle. And now we've changed something that we didn't know into things that we do know. So it'd be a good idea to draw your special triangles. So I'm going to do my 60-degree angle. So if this is 60, this is 30, I've got 1, 2, root 3, double checking, should anything be negative? Nope, it's in the first quadrant. So the sine of 60 is opposite over hypotenuse. So the sine of 60 is root 3 over 2. And then the cos of 45. So now we need to draw another triangle with a 45 in here. So I know the 45 is my 1, 1, root 2 triangle. So again, nothing needs to be negative because it's 45 in the first quadrant. And so cos is adjacent over hypotenuse. So it's going to be 1 over root 2. Now, if you want to rationalize at this point and put it in as root 2 over 2, totally fine, totally up to you. I'm going to just do that for now, although I'm having second thoughts. But anyway, we'll keep going. Then we're going to do minus the cos of 60, which is adjacent over hypotenuse, which is 1 over 2, times the sine of 45, which is opposite over hypotenuse, which is 1 over root 2. Okay. So again, you could have written this in as root 2 over 2 instead of 1 over root 2, because we will end up having to rationalize. But if you didn't, and you were at this point here, let's just keep going. So I'm going to simplify this by multiplying. I end up with root 3 times 1, which is root 3, over 2 root 2, minus 1 times 1 is 1 over 2 root 2. Now I'm going to subtract. I already have my common denominator of 2 root 2, and I'd have root 3 minus 1. Now, because I didn't rationalize yet, now I have to rationalize. So I'm going to multiply by the radical in the denominator. I would end up, so you're going to distribute that root 2. You would end up with root 6 minus root 2 all over 2 times root 4, which would simplify to root 6 minus root 2 all over 2 times 2, which is 4. And thankfully, that is done. Okay, now what? Well, let's try another one. So let's do this one in, well, we have to. Let's do this one in radians. So we've got 5, 5, and 12. So what I'm going to look at is the fact that I knew 0, 30, 45, 60, and 90. Well, those aren't very helpful when they're written in degrees. So let's write them in radians. We've got, well, yeah, we've got 0 radians. We've got pi by 6, pi by 4, pi by 3, and pi by 2. Okay, so that's what they are in general. But what I want to look at is them with denominators of 12, because then it's easier for me to see, well, what combination could I use to make 5 pi by 12? So I'm going to write those again with denominators of 12. So this would be 0. This would be 2 pi by 12. This one would be 3 pi by 12. 4 pi. Why do my all 4s always turn into 9s? 4 pi by 12. And then lastly, 6 pi by 12. Okay, so what combination could I use to get 5 pi by 12? Well, the only combination I see right now is 2 pi by 12 plus 3 pi by 12. So I'm going to replace this with the cos of 2 pi by 12 plus 3 pi by 12. Now, those aren't really useful for me because I can't remember which one's which. So I'm going to change that back to pi by 6 plus pi by 4. Okay, then I go back to my trusty formula sheet, which I'm just going to move to the other side of the page. Okay, and then I'm going to look at this and be like, okay, so now I'm talking about the cos identity. So now I'm going to look at this one. Okay, and it's the cos addition identity. So the cos of an angle plus another angle, I'm using the top, is equal to the cos of the first angle times the cos of the second angle. Now look at how this is flopped. When you have an addition, you're going to be subtracting in your expansion. So this will be cos of the first angle, cos of the second angle, minus sine of the first, sine of the second. So let's write it. We're going to go cos of the first, cos of the second, minus sine of the first, sine of the second. Okay, now unfortunately we didn't use 30 degrees in the one before, so we got to draw triangles again. So let's draw 30 degrees. Pi by 6. Pi by 6 gets the 1, 2, root 3. And then let's draw our 45 at the same time, although we do already have that one. Pi by 4, 1, 1, root 2. I find the more often you draw those, the less likely you are to forget them. All right, so cos of pi by 6 is adjacent over hypotenuse, root 3 over 2. And then cos of pi by 4 is adjacent over hypotenuse, so 1 over root 2. Now, 1 over root 2, let's try rationalizing first this time. So I'm going to write this as root 2 over 2. Save myself a step. And then we've got sine of pi by 6, which is opposite over hypotenuse, which is a half. And then the sine of pi by 4, which I'll use the root 2 over 2 again. Okay, now what? Well, simplify. So we've got root 3 times root 2, which is root 6 over 2, minus 1 times root 2, which is root 2 over, sorry, those are over 4. Don't go so quickly. This is why I miss having you guys when I'm making these videos. Somebody would have stopped me. So for this one, I've got root 3 times root 2, which is root 6 over 4. And then I've got 1 times root 2 is root 2 over 4. Now that I have a common denominator, I can rewrite it as root 6 minus root 2. Oh, look at that, over 4. You often get the same answer. I'm yet to find out a predictable pattern for knowing when I get to which one, but there's only a few combinations you can get because we're only dealing with 0, 30, 45, 60, and 90. And 180 or whatever we wanted to within there, but there's not a lot of combinations that you can get. Okay, so this would be a great place for you to pause the video and give the next 2 a go. So I've got one with degrees and one with radians. And then when you come back, you can unpause and I will work it through. Okay, maybe you stayed because maybe you're not feeling really great about this, but we're going to give these ones a go. So this one, I kind of kept it too similar, but let's do cos of 60 minus 45 again, because we've already done all that hard work above. So hopefully you looked at your formula sheet. You saw that the cos subtraction identity, you go cos, cos, sine, sine. So it's going to be cos of 60, cos of 45. Now, because it's a minus, you should get a plus in your expansion, right? It switches. And then you're going to have the sine of 60 and the cosine of 45. Okay, let's keep going from here. Now, we already figured out the cos of 60 up here. Cos of 60 was 1/2, right? We've got cos of 60 was 1/2, so I'm going to write 1/2 in here. Cos of 45, I'm going to put it in rationalized as root 2 over 2. Then we go sine of 60, which I have right here. So I'm going to go root 3 over 2. And then the sine of 45 is root 2 over 2. All right, and then let's simplify. So I end up with 1 times root 2 is root 2 over 4, plus root 3 times root 2 is root 6 over 4. Look at that, a common denominator. And I end up with root 2 plus root 6 all over 4. And we call it done. All right, the next one is sine of 7 pi by 12. Now for this one, I'm going to have to go back up to my denominators of 12 and see if I can make 7. So this time, I'm going to do 3 pi by 12 plus 4 pi by 12. So this would equal the sine of 3 pi by 12 plus 4 pi by 12. Then I'm going to rewrite that as the sine of pi by 4 plus pi by 3. Okay, and then we do our expansion. So for sine, it goes sine, cos, sine, cos. So I'm going to do the sine of pi by 4, the cos of pi by 3. Now you match the sign, so plus, and you switch the cos of pi by 4 times the sine of pi by 3. And then we go. So I already know that the sine of pi by 4, because we've used it so many times, is root 2 over 2. Now pi by 3 we haven't done yet. So I'm going to draw pi by 3, which is the same as 60. So I know that it's goes 1 is across from pi by 6, 2 is your longest side, and root 3 is always across from 60. And I like it in radians, right? Pi by 3 is across from root 3. It's not a coincidence. Well, kind of. Okay, so then I'm going to figure out my cos. So my cos of pi by 3 is 1/2. And then we keep going. So the cos of pi by 4 we already know is root 2 over 2. And then the sine of pi by 3 is root 3 over 2. All right, that gives me root 2 over 4 plus root 6, oh, so repetitive, over 4. And then I end up with root 2 plus root 6 over 4. All right, moving on. So now that we've gone forwards, we also want to be able to go backwards. And what I mean by backwards is that they're going to give you an expanded trig expression, and they're going to ask you to do the following. Express as a single trigonometric expression and evaluate. So hopefully you're kind of getting used to the pattern now. If you look at this one, you should see sine, cos, cos, sine. So I know that this is the sine sum and difference identity. Sine, you always match the sign. Ooh, there's a nice little way to remember it. Sine, you match the sign. So if it's an addition, it ends up as an addition. Okay, and then 70 is your first angle and 20 is your second angle. So why did they ask me 70 and 20? Well, because if I add 70 and 20, I get 90. All right, now there's lots of ways of evaluating the sine of 90 degrees. You know, way number 1, 90 degrees is up here at 0, 1. I know that sine is y over r. All this information that can't leave your brain. So the y value is 1, the radius is always 1, so I know that sine is 1. Way number 2 is that you draw your trig function, right? This is pi by 2 here at your second key point, and it has a y value of 1. Okay, so anyway, you do it, you evaluate sine of 90 as 1. All right, pause the video and give this one a go. Okay. So hopefully you looked at this one and you saw cos, cos, sine, sine. That means that we're dealing with a cos sum or difference identity. Cos is contrary. I was trying to think of something funny. I don't know. But whenever the sign is in here, yes, switch it. Okay. So then you do the first angle, and instead of being addition, it's subtraction, the second angle. Okay, let's see what happens with this one. So now what I'm going to do is I'm going to subtract these two. Now to subtract fractions, I need a common denominator. So pi by 6 minus pi by 3, I'm going to make that 2 pi by 6, which is going to give me negative pi by 6. Okay, so this is going to be expressed as a single trig expression as the cos of negative pi by 6. Now this one, these were actually exact to begin with, so you could have evaluated this, but the question said to write it as a single trig expression. So I've done that. So I'm going to evaluate this guy. So since it's negative pi by 6, that tells me it's in quadrant what? Right? Because it's negative, instead of going counterclockwise, I'm going to go clockwise, and I'm going to go down. This is negative pi by 6. But the nice thing is nothing else changes. 1, 2, root 3. Okay, well, I guess those things don't change. But always check to make sure if anything should be negative. And this one, because it's in the 4th quadrant, the y value is negative. But I'm evaluating cos, so I got off lucky. So I get adjacent over hypotenuse. So even if I forgot that negative, I'm still fine. Awesome. All right, the last one. So this one's a little bit different, and it seems intimidating, but it's very similar. You just don't have to know your special triangles. So what it is they tell you what sine theta equals, and they tell you what sine beta equals. Now they often put it between 0 and pi by 2. That way you don't have to worry about any negatives. If they ever tell you that it's not in quadrant 1, then watch out for negatives. But what they're going to ask you to do is evaluate sine beta plus theta. So when it's beta plus theta, like you can't just put 2/3 and 1/2 in, because this isn't the value of theta. This is the value of sine theta. This is the value of sine beta, and this is not sine beta plus sine theta, right? You can't, even though it looks like an expansion, trig doesn't work that way. It's the sine of an angle, not the sine times an angle. So you have to know that any time you have something like this, where it is in sum within the, I lost my words, angles, right? You have to use your identities. So this is the sine addition identity. So it goes sine of the first angle, cos of the second angle, match the sine, and then it goes cos of the first angle, cos of the second angle. All right, now we can evaluate. Well, we know that the sine of beta is 1/2. Well, they didn't tell us the cos of theta. They didn't tell us the cos of beta. But they did tell us, oh, sorry, I wrote cos there. That was supposed to be a sine. The sine of theta. Okay, so they didn't tell us the cos of beta, but they did tell us the sine of theta is 2/3. But we're missing cos. So what are we going to do? Well, we know that this angle is between 0 and pi by 2. So let's draw it. If this one's theta, we know that the opposite is 2 and the hypotenuse is 3. All we're missing is the adjacent. Well, how are we going to find it? It's a right triangle. So we're going to say 3 squared is equal to 2 squared plus, let's call it x squared. So I also could have said x squared is equal to 3 squared minus 2 squared, right? I'm solving for a side length, not the hypotenuse. So let's keep going. X squared is equal to 9 minus 4, which is 5. And then x would equal, when we take a square root to get an answer, technically there's 2 possibilities, plus or minus. Because it's in quadrant 1, I know that it's the positive root 5. So in here, I'm going to go positive root 5. So now I know for theta, the cos of theta is adjacent over hypotenuse. So it's going to be root 5 over 3. All right, we just have to do the same thing for beta. Okay, it'd be a good idea to pause the video now and see if you can give this a go. So beta, the opposite is 1, the hypotenuse is 2. This is seeming an awful lot like a 1, 2, root 3 triangle, but if you don't trust yourself, double check. So let's call this x squared again. It's equal to 2 squared minus 1 squared, which gives us 4 minus 1, which is 3. And look at that. X would equal plus or minus 3 root 3. Because it's in quadrant 1, we know that the answer will be positive root 3. So we use root 3. Okay, so the cos of beta is adjacent over hypotenuse. And then we just simplify. So this is 1 times root 5, which is root 5 over 6, plus root 3 times 2 is 2 root 3. Oh, common denominators. They always end up this way, and it's lovely. Okay, you end up with root 5 plus 2 root 3 all over 6. Whew. All right, so those ones are a bit trickier, but they're kind of fun once you get into them, although I think everything's fun, so I probably sound like a broken record, but good luck.